Hello there, and welcome to Preprints in Motion, a podcast taking a deep dive into the fast-paced world of preprints.
Join us as we sit down with early career researchers, discuss their latest preprint, and find out about their journey through the muddy marshes of academia.
Hit that subscribe button, leave a rating, and find us on Twitter at MotionPod. Support us by heading over to buymeacoffee.com/preprints. But for now, let's get into the show.
This week we discuss heart regeneration and liken the publication system to selling strawberries with postdoc Avraham Shaked. We do microscope training this afternoon, but it went on a lot longer than I thought it was going to go on, because one of them broke.
This is the case with a lot of things, science. I find it's very hard to kind of take care of your time management in science because so much is unpredictable. It's very hard. Like when I'm being asked by my wife, like when I'll be home, I'm like,
whenever.
I'll give you a range of like 4 hours either end, and It's very hard. Yeah,
never on time since I started science, ever.
Good to know.
Right, let's just do it. So I really want to talk about you wanting to be a chef and how similar that must be to a career in science. But I think we'll save that until the end bit when we talk about careers, because that's really interesting.
Okay,
so I guess we'll start with a different fun fact. So you ran 7 marathons, which I think is very impressive. But you can also trace your family origins back to like the 1700s, that must be pretty cool. Did anyone do anything particularly exciting in the time?
I think it was just the fact that my dad picked up the idea of family genealogy. He got very into it. He's still big into computers, but I think technology's sort of come a long way. But he built back in the 90s some sort of you would now say is a very dated family tree, where everything is sort of looks very binary, and it's not like a tree, it's more computer code. But I think as scientists, we're very good at looking past things that aren't always aesthetically pleasing and getting into it. When you sort of get past it, it's really cool to just see how many generations back, he managed to sort of speak to people and trace it back. And it's just cool when you look at these sort of dated documents and you're like, oh, wow, we were there.
Yeah, I've no idea about my history at all. It stops at like grandparent level for me. That's it. That's all I know.
Yeah, no, I'm trying to pick it up from him as well, and it's kind of awkward because you want to have conversations with people in your family who are quite old, but you kind of don't want to introduce it in the way that's sort of like, I want to kind of talk to you before but you kind of really do want to talk to them before. But yeah, no, it's a nice way to get into history, just because you feel a lot more connected to it.
That's weirdly coming back around to my morning. So I start off each morning listening to Radio 4, because apparently I'm middle class now. And there was someone on there this morning talking about how they go into hospices and they kind of do like an autobiography of people while they're in there. Just the random person, not famous people, none of that stuff. And yeah, it was just really interesting that you can just get someone's full life story, and to record it is something we miss a lot of the time.
Yeah, absolutely. Yeah, no, I sat with my dad and his 12-year-old brother, and I just hit record, just had a conversation, and it's great. I would encourage people to do it.
Well, there you go. Look at that. So history start. It's getting into preprints and science. That's what we're here to talk about.
Yeah.
Why don't you give us a little overview of the preprint we're here to talk about? Sort of what you did, what you found, and then we can ask all the difficult probing questions that we definitely are known for on here.
Absolutely. So the lab that I did my PhD in was primarily involved and interested in cardiac regeneration. And previously I had been interested in the subject as a whole. And I sort of joined the field when kind of most people were already quite good at heart regeneration. I mean, as a starting point, the heart is a great organ to do regenerative studies on because it's really bad at regenerating. It's the pits. So it's a good starting point. And there was a big, I wouldn't say controversy in the field, but there was a lot of discussion for many years as to which was the best way to get the heart to regenerate. Was it through promoting a stem cell source, or was it through taking the mature cells of the heart, the cardiomyocytes that perform all of the contractile function, and trying to essentially reawaken an embryonic program in them to a time when they could regenerate in order to achieve this? And that's essentially it ties back to the reason why the heart is such a bad regenerative organ, is because one, it doesn't have this stem cell niche, or if it does, they don't really do a lot after injury. And then the only remaining cell source that you have don't divide. So they divide at extremely slow rates. So they're very reluctant to do so. And when I joined the field, a lot of people actually got quite good at overexpressing various mitogens in these cardiomyocytes in a way to promote them to divide after injury and have a regenerative response. And so my question focused about this question around, well, if you take a mature cell that's hyper differentiated in terms of excellent specialized function but terrible ability to divide, and you force it to divide, you kind of push it back up its lineage, then when you sort of let go of that stimulus, does it go back fully, or does it go back partially, or does it not go back at all, or has it gone back in a different direction? So that was the sort of context in which we looked at it. Like if you pull a spring, if depending on how far you pull it, it might never go back, it might go back fully, or it might go back partially. That's kind of how I thought about it, especially if this is the tack that we're going to take in humans and hopefully bring it into the clinic at some point. You'd hope we would address this sort of, are they really the same afterwards? So my lab already had a system when I joined that was a sort of an on-off switch to get cardiomyocytes to divide. So my study was essentially saying, okay, well, let's turn it on for a few weeks. Let's turn it off for a few weeks, this mitogenic signaling in the cardiomyocytes. And let's just throw these hearts to RNA-seq and proteomics at different time points along this along this experiment, and just see how much do they go back to a heart that you didn't do anything to. So the main thing that we found was essentially that at an RNA level, things look pretty good. But when you look at the proteomic level, you actually find that there's sort of like a residual dedifferentiation in these cardiomyocytes or in the heart as a whole. And so essentially the answer is they almost go back to normal, but there's that little bit that they don't quite. That was sort of the first major finding of the paper. And then there was a lot of debate in the lab that kind of it split the lab in terms of, was this good or bad? Because there were some things that you could look at this heart and you could say, a mature heart really ought to have gap junctions, which are, one of the major connecting parts between cells in the heart and is thought to play a very important role in electrical communication in the cardiomyocytes. And these hearts that have undergone this sort of dedifferentiation, redifferentiation, they tend to lack sort of connexin proteins. So some people looked at that and they said, well, that's just awful. Those mice are sick. And other people looked at it and they looked at the whole proteome and they said, wow, these mice look rejuvenated, which sounds a lot better. And so then we decided the best way to test this out was to perform this sort of dedifferentiation, redifferentiation in uninjured mice, just as a biological process, and then to injure them afterwards to see, if you apply a stress to the system, can you tease out a difference between these two groups, which, before you had injured them, there was no difference. And one of the things that I was really surprised to find is that these mice seemed really protected against injury of the heart, which we boiled down in the paper either to the fact that they were rejuvenated in a sense, and so younger hearts are more robust against this sort of ischemic damage, but also the fact that they lack these gap junction proteins. Perhaps is sort of my favorite theory, is that when you have a heart injury, there's the ischemic event where cells die because they have a lack of oxygenated blood, but then there is a wave of necrosis that sort of spreads from those initial dying cells. And one of the ways that they do that is through gap junction proteins. And so if you don't have them, you actually have kind of disabled that second mechanism of the wave of necrotic death. We didn't show this in the paper, but this is sort of my favored theory of what's happening.
You're touching right upon what I'm currently working on, which is great. Didn't see that one coming. So I'm working at neutrophils following ischemic reperfusion injury.
Right.
Eventually in the heart. Immediate obvious question. Have you looked at the immune response following this whole process? Is that different?
We didn't look too much into it. It was one of those things that I think, this was sort of like a 4 or 5 year study, and only towards the end of it did I start kind of looking back at the data and seeing, the immune system gets heavily involved when you push these cells to divide, and they seem everything seems to calm down. So there's definitely some inflammatory response during I wouldn't call it regeneration, because we did it in a system without injury. We just turned on the mitogen, turned it off, but that definitely recruited a lot of immune cells, at least from our transcriptomic and proteomic data, and it mostly returns. how it's affecting the neutrophil specifically, it's to be determined.
Yeah, I so many questions, but we did an immunology episode last week, or we will do as these go out. So I'm gonna stop.
No, it's definitely something I think I'm appreciating a lot more. Everywhere I seem to turn now, it's immunology,
Everywhere.
and I think, oh my goodness, I really have to start learning about the immune system a lot more.
Can't get away from it.
Yeah.
It's the best system. So one of the things that's really nice to see here is that you have looked at RNA and protein, which so many people just neglect to do, and they pin everything on an RNA-seq experiment and claim the whole world has been solved of all of its problems. So it's really nice that you've looked at both. Was that just you have loads of money to throw at a problem, or was this I assume this was a very conscious decision to really try and tease out what's different? And what kind of explanation would you give for some of those differences you saw? Because you said there's still some residual differences at the protein level, whereas the RNA level, it was kind of a bit calmer.
Yeah, the thinking behind it was more deliberate. It was known quite a few years ago that RNA does not necessarily equal protein, and it was the outset of a big project. So it was sort of, if we're going to tackle this, let's just do it right once at the very beginning. I wanted it to be even more. So I wish it was a no expenses spared experiment, but the proteomics we had to do was the light version. So it wasn't a sort of a highly deep assay, and I wanted to do phosphoproteomics. I mean, you can get carried away when it comes to the proteomics because there's so many different post-translational modifications that make this stuff interesting and so much more complex. So I wish it was throw everything at, but my PI said I can't be accused of going on too much of a fishing expedition. So I said, okay, well, I'll get what I can. And also, it was 3 different time points over an injury condition, a non-injury condition, at least 4 mice per time point. It got like 64 samples that we were sending to mass
expensive.
So it was, I think it was expensive enough. So I wasn't able to push it too much more. But I'm glad we did. I'm glad we did, because we did see that there were differences between them. As to why, that honestly, it's something I don't know the answer to. The one thing I can say is that, firstly, for one thing, it's several steps of regulation on. So we actually thought at one point it might just be a timing factor. RNA, it's quicker for things to get back to normal, but proteins, they have different levels of stability. And again, they're just further away from the origin of the process. And we actually did one experiment to suss that out. So again, going back to the connexin 43, the connexin that joins cardiomyocytes that we saw when we expressed this mitogen went down. And so we said, okay, well, after 4 weeks of recovery, we didn't see them recover. They stayed down. And we said, okay, well, if this is something that just you need to give it a little bit more time, we thought, okay, so we waited 5 months and a year, and we looked at those mice, and we saw it didn't recover. So that was sort of, again, we didn't know why, but it definitely seemed like the explanation of, oh, well, it's a bit further from the origin of the process, and if you give it more time, that doesn't really stand up. It seemed to be a truly irreversible part. With respect to that one protein, that's the only thing that we actually assayed for this 1 year after switching off business. When the human heart develops, it can take many years for this protein to actually get fully localized to the gap junctions in human hearts. So it might be something that physically in the lifetime of the mouse just wasn't going to happen, but it seemed like a pretty profound irreversible effect, which we kind of didn't want to go out and sort of be sort of alarmist in terms of, guys, there's something wrong with the regeneration strategy in the heart that we're taking. But so many papers we found were really just focusing on the sort of, let's get cardiomyocytes to divide, which in itself is amazing because for so many years they were thought to be post-mitotic. So a huge amount of effort went into that. And it's not to undermine any of the efforts that went into that, but we did want to sort of say, are they really the same afterwards? So I was kind of happy to find out. It makes it a bit more challenging. Yeah. And the other reason I was happy to find it was, again, not because I wanted to find it, but the field of heart regeneration, as I alluded to earlier, at the time when people weren't sure what was really the mechanism behind it, some clinical trials were started in humans that involved the injection of stem cells, either into the regions near the heart or just IV. And I mean, the findings were modest at best. And so there were some retractions that came out after it was found that, stuff had been falsified. It did a lot of damage to the field. And one really good paper came out saying that the reason that there was some modest benefit to this was the innate immune response to these cells being introduced into the system helped the heart deal with the damage. So anyway, I think the relationship between clinicians and academia was damaged in this field and it's taken a long time to recover. So that's kind of the other reason I was sort of intrigued to do this study, because if we're going to do that again, we really have to make sure the process from end to end is really well understood.
I like that it all comes back down to the immune system again.
Yeah.
So you take cells, you de-differentiate them, then you redifferentiate them. How does those redifferentiated cells compare to just a young heart? Did you look at the transcriptome or proteome of young hearts to these redifferentiated hearts?
We hadn't actually. I think that's one of the questions I'm pretty sure is going to come back from reviewers, if I'm being honest. And I think it's something that we'll probably look a little bit more at. I'm not entirely sure. I think this use of rejuvenated is it's a nice term, and I like it because it is useful in describing the fact that there are some characteristics of these mice that I would say kind of have a hangover from the embryonic signature. The thing is, even a young mouse that's sort of 2 or 3, I mean, these mice tend to lose their regenerative capacity in their heart by 7 days. So I think even if you look at a 2-week, 3-week, 4-week-old mouse compared to the 3-month-old mice that we use, you might not find huge differences. And I would say there are sort of lingering elements of an embryonic state, which kind of it sounds more extreme, but in terms of practicality, or in terms of empirically, when we injured these mice, they did quite well. Whereas if you injure a 2 to 3-week-old mouse, I'm not sure how well they do. So yeah, but it's something that could come up, and we would probably have to check that.
Yeah.
So it depends what you mean by rejuvenation. I mean, like really rejuvenate.
Look at us asking the reviewer questions.
That's what it's about.
So maybe we should take a little bit of a step back and just talk about the model you're using to de-differentiate and redifferentiate a little bit. Could you explain how that's working for those of us not overly familiar with any of the genetics?
Sure. So the way that this was originally done is a postdoc in our lab many years ago now was actually looking into papers that used the cell surface receptor ERB2 or HER2 in humans, and it was being used to de-differentiate neurons, also for regenerative purposes, because in many senses the nervous system is very similar to the heart in that you have hyper-specialized cells. They don't readily divide, and any injuries to the central nervous system are devastating, and you don't see a powerful regenerative response. So he noticed that some people had forcibly overexpressed an active form of ERB2 in these neurons and found that it was capable of making them divide and lose their specialized function, so temporarily de-differentiate. So he engineered a system where, and I think to his credit, he kind of saw in advance that this would have to be a transient system. So he engineered what we call in the field of transgenics a TET-off system. And the way it works is you have 2 transgenes that kind of work together to allow you to turn this gene on in the cardiomyocytes and turn it off by adding an antibiotic to the food of these mice. So essentially, these mice, when you give them the antibiotic, behave as any other normal mouse. And only when you want to, if you remove this food and you give them a normal diet, they will start expressing this activated form of ERB2 in their cardiomyocytes. And then when you want that to switch off, you just add the food with the antibiotic again, and everything in terms of the expression of this protein calms down. And the reason that he looked at ERB2 was not just because other people had shown that it could make cells that don't divide again, but because, I mean, this was known since 1995 that the cardiomyocytes undergo cell division in order to grow when they're embryonic. And shortly after birth, they exit the cell cycle. And one of the genes that is critical to that is ERB2 and its its co-receptors and ligands. So he engineered a form of ERB2. I think he took a form of ERB2 from a rat model. There was essentially an ERB2 that did not need a ligand to bind it in order to elicit cell signaling for proliferation. So he kind of simplified the system. He just said, you just need this activated form of ERB2, and he engineered a transient switch so you could turn it on and off at will. And that was really what, when he first did the study, again, the focus of his paper was more on, wow, cardiomyocytes were forced to divide in an adult mouse where they just don't do that for a regenerative response. So I saw that system, and I thought, that's a pretty neat way to study the second half of the way I see it is it's sort of the second half of the process. But that's how he got to looking at ERB2 because of its natural role in cardiomyocyte proliferation in an embryonic heart. So it's almost like to reactivate the latent capacity of a cardiomyocyte to divide.
Yeah. So when you did your transcriptional and proteomic analyses, what kind of pathways were coming out to suggest that things were leading more towards this sort of happier state of affairs?
Do you mean in the sense like which pathways were going back to normal or being going different in the first place?
Yeah.
Sure. Yeah. So it was something that we already, I think, through literature searches, had a good idea of where to look at in terms of what are the main things that change in a cardiomyocyte when it shifts its behavior to a more proliferative state. So obviously, one set of Go terms that came up a lot was involved in cell cycle activity. So that was sort of one bunch of Go terms that we put together. We then also saw a lot of metabolic changes, which is something that we were quite familiar with. And it goes well beyond the heart field, that cells that are more glycolytic or have a preference for glycolytic metabolism are better suited to dividing. That's true of cancer cells. That's true of cells in the heart before the mouse is born or before a mammal is born. They're in a low oxygen environment. So their metabolism is less oxidative phosphorylation and more glycolysis. So again, that's very amenable to cell division and not so amenable to sort of high impact constant contraction, which is sort of what the adults do. And the third thing that we looked at was cytoskeletal arrangement, which I suppose it's important for any cell that's undergoing division, but these cells are also having to partially deconstruct their complicated contractile machinery, which is a very specialized form of cytoskeleton. So they somehow have to sort of pack that all down, then start assembling microtubules to start their division. And there's also an element of migration whereby you have a scar being deposited and you need to start moving into that scar tissue as it degrades. So we looked at sort of all sorts of Go terms that were to do with motility and changes in cytoskeletal architecture. So we kind of grouped those three just based on our experience and sort of, we essentially grouped any Go term into one of those three. And then we also had a fourth one we looked at that was heart function. So it could be anything that was not really fitting to those three, but more specifically to do with heart, like calcium signaling. We had come up gap junction signaling. It's not solely to do with the heart, but in this case, it didn't really fit into the other three. And so when we plotted the behavior of those three sort of meta groups of Go terms in our proteomic screen, we saw that they were very much changed when the cells were in a state of division. And then when you turn things off and you allowed the cells to redifferentiate, they started relative to a wild type mouse, go back to normal, where you couldn't really detect these Go terms as being differentially activated or not, except for the proteomics.
Yeah.
They're a bit.
I'm glad you mentioned heart functions, because that was my next question. So have you looked at how the heart is actually functioning following this redifferentiation? Is it functioning better than it would otherwise?
So that was our starting point, which was that the short answer is yes. They look very similar. And the way that we typically assess that in the field is we use echocardiography, which is ultrasound, very similar to when you're looking at a baby in the womb, but we do that to anesthetized mice, and you're able to sort of place it over their shaved chest and you get a nice video of the heart beating. So, when you take that approach and you can measure all sorts of different metrics related to heart function, you can see that, when the cells are undergoing their division, the heart function decreases. And then when you switch things off, you see this recovery phase. So redifferentiation in the way that we see it is not merely transcriptional and proteomic changes. It was actually first noticed years ago as something that we saw functionally. We didn't see improvement in heart function until you switched off ERB2 and let the heart essentially enter this phase of redifferentiation. And I think one of the things that we were curious about in this study is to say, phenotypically, if we go beyond echocardiography, can we see changes in the redifferentiated heart? Because, most groups really use echocardiography as their gold standard. And now somewhat MRI as well. which is really nice. It doesn't have as many as sort of the shadows that you get in echocardiography, and you can get a slightly more accurate.
Is it a teeny tiny MRI machine? Because that's what I'm picturing in my head for a mouse.
I've never been into the room, but I think even a teeny tiny MRI machine is huge.
Quite
big. But the thing is, echocardiography, MRI, they both rely on the mouse to be anesthetized. So you're always looking at some sort of system that can be subject to artifacts where you can either have ceiling effects or floor effects, because you depress the heart function a lot when you put these mice under anesthesia. So I wanted to kind of find all sorts of different ways, and over the course of my PhD I was unsuccessul in looking at different ways to measure cardiac function in a way.
Sounds like mice. A PhD, yeah.
Yeah, I spent many hours and days in dark rooms running mice on treadmills and whatnot. But it's a very noisy assay, and I wouldn't recommend it. But so one of the things that we decided to look at is we said, look, if these gap junctions are differentially expressed, even when by echocardiography these mice look great. After redifferentiation, you look at echocardiography, the mice look exactly the same in terms of their videos. When you look at them, we teamed up with a group that were very good at measuring the wave of electricity across the surface of the heart during a contraction cycle. Is that sort of typically how the heart beats in a wave of contraction? So, and we thought, since we have a protein that's downregulated, involved supposedly in this process, then we should see something. We actually saw the opposite of what we were expecting, which is just classic science. Yep. And it raised a lot of questions of, if this protein is important in electrical communication and you don't have it, why is your conduction velocity faster? That's essentially what we found, is that the speed of electrical communication increased despite this protein that everyone seems to think is involved with speed went down. So it's sort of like, well, how did that happen? So it's really a case of, I think, just digging into the literature and seeing that apparently it's more complicated than that, and there are many different proteins that can mediate. We didn't provide the explanation for it. I got questioned about it a lot, and I found that there's all sorts of different proteins that can mediate this. And even in knockout mice, you have to go, I think, a reduction of more than 90% of this protein before you see a change in the conduction velocity, which kind of calmed me down a lot, because we only saw a 75% reduction. So I was like, okay, this is somewhat within the bounds of what other people have seen, even if it's still quite a bit different. But again, I think the main point that we took away from this was sort of like, hey, these hearts, when you measure them by echo, seem the same. But if we dig a little bit further, there are some very real phenotypic differences. The point was that it's not just a quirk of proteomics. This is something that we were able to measure phenotypically and see that something that is critical to heart function is different. Even if it's not necessarily worse, we kind of just wanted to say that these mice aren't the same. And we need to be aware of these changes as we sort of develop tools and techniques to study regeneration, so that when we're ready to move into humans again, we can do it with a lot more knowledge and a lot more sort of, well, how are we going to account for X, Y, and Z, given, things aren't always going to be the same afterwards.
Yeah. So these gap junctions have come up a fair bit now. Are these things you can modify directly? And is this something you've done or planning to do?
So it's something actually I discovered in sort of reading after we had these results of the better survival of these redifferentiated mice, is I found actually there's a whole field that look into gap junction therapeutics, where they essentially get gap junction mimetic peptides that essentially behave as gap junctions or gap junction blockers. And some people have shown some really promising results where they essentially treated mice with a gap junction peptide blocker that either causes them to sort of not cluster, but rather become dispersed and they don't really carry out their function anymore. And to show that actually when you injure a mouse after that, you get limited damage, because the necrotic signals can't pass as much. And there's a whole field of different sequences of peptides that people are testing out and looking into and stuff like that. So, unfortunately, since we posted this, I've now moved on and started my postdoc. So when you say, am I planning to do any more on this? we collectively will definitely be looking into this. I think it's a very interesting thing that we stumbled upon. But it's a question of, I think, finding the right tool and testing it out.
And how long does the protection last for? Do you know? So if you redifferentiate some heart cells, can you injure them months later and they still heal better than non-redifferentiated hearts?
Well, I'm very glad that you asked that question.
It's what we're here for.
Because not because unfortunately I have anything that I can tell you yet, because the experiments are ongoing by someone who's sort of picking up the project and running with it as we sort of head into revisions. But that was the next logical question that we were thinking about. What are we going to be asked on? But also, if we've got this really exciting effect, how long does it go for? And if the gap junctions are anything to go by, then it really should be up to 1 year. So we've got mice that I redifferentiated or started redifferentiating about 6 months ago. So they're now in the process. And there's a few cohorts behind that we're not really sure whether we're going to go for the 1 year or just keep it at 5 months. I think if we see a good effect at 5 months, I think we'll take that.
Yeah. Nobody wants to wait a year.
Right.
So taking all of this together, where do you see this going in terms of potential treatments?
I found that during the course of my PhD, even though the strategy of getting cardiomyocytes to divide, or sort of forcibly to make them divide, was probably the most powerful and the most truly regenerative, it often falls by the wayside because of its clinical concerns, most obvious of which, as I sort of got told in group meeting, quite often, was you're giving cancer to the heart. and I always answer back that it's a mitogen, not an oncogene. But then, depending who you talk to, ERB2 is an oncogene. But I think so does every mitogen have that capacity. The scary thing is the idea of a clinician essentially getting someone's cardiomyocytes that aren't really supposed to be dividing to stop beating and dividing. And those words themselves sound terrifying. I mean, when you see the mouse that's actually actively expressing ERB2 in its heart at higher levels, it still beats. And there's no outward clinical sign that these mice aren't doing well. It's just by echocardiography, their hearts are a bit chubbier, the cells get larger temporarily. So clinically, that approach itself is not perfect. But other mitogens that other groups have looked at don't always cause hypertrophy. They probably just cause a temporary reduction in. It's not a complete abolition of function. It's just, I think when you explain it in terms of it can either contract or divide and not two at the same time, it sounds a lot more dramatic than it is.
Yeah.
But a lot more sort of feasible things to get into the clinic are things that have cardioprotective effects, things that modulate the immune system, that sort of thing. And the groups that are really pushing cardiomyocyte division or transient cardiomyocyte division, they're definitely a little bit behind, but they're getting there, because again, it's riskier, but it has the better final outcome because it's truly regenerative. Even the people who are looking at modulating the immune system, you can change the scar format, but you're not going to actually get more cardiomyocytes that you need to be in that place. And so one of the things that I was I would be very keen to see sort of coming out of this particular research is that the way I see it is, even when you injure a mouse and you give it a course of ERB2 or you give it a course of any other mitogen, and then you switch that off or you take it away, I don't think I've ever seen an academic paper where they completely abolished the scar. There's always some left, right? These things aren't perfect. They're good and they're getting better. But the way I see it is, nonetheless, eventually you will see these things in the clinic, because I think, as you probably know, when patients are in a really bad state, right, and you say, listen, you can either have this regenerative treatment in the heart that might give you cancer in 5 years' time, or you can carry on with your heart that might clock out in 1. So I imagine, as all of these sorts of therapies do, the first uses will be in the highest risk cases. But what I assert, not to be scientific fact, but to be definitely something that I speculate is true, is that it is better to use this transient mitogenic stimulus sort of as a prophylaxis against disease. Why? Because the damage that is incurred is far less. It's better to incur less damage rather than to repair a huge amount of damage, even if you can repair it quite well. So the way that I would really be intrigued to see this is sort of in larger animal studies. Typically, we work in pigs. Is to essentially basically ask: is the damage better when you give them ERB2 for a bit before and let them calm down, and then injure them, or if you injure and then give them ERB2 afterwards?
Yeah.
I suspect they'll fare better, at least by echocardiography that I've seen in our own hands, with the prophylactic approach. And the only way that I think we'll ever get there is once clinicians become sort of a bit more comfortable with this idea, after it's been done a few times in humans, then the idea of prophylaxis for maybe the highest risk patients will become something that they can even stomach. But, when I said this to my supervisor, he laughed me out the room. He was like, no one's even doing that in patients after a heart attack. You want to do it before. So I'm holding out, but I reckon it will be a very long time.
Well, you touched upon the last question I had there as well. So I'm done with the science questions.
Where do I find out about the different bioarchive licenses? This CC, BY, CDXY nonsense is driving me nuts.
ASAP Bio have a resource for that.
Ugh, that's your answer to everything.
That's because they have everything you need to know about preprints.
Sure, they probably have the basics, like info on the preprint servers, but what else is there?
There's so much more. Looking to post a preprint but not sure what different journal policies are? They have a collection to help you out with that. There are meetings around preprints and associated services. If you want to know how preprint adoption has changed over time, there's even a page on that.
And COVID?
They have a big section on preprints and the pandemic, plus some really cool infographics for communicating preprints.
And university policies? Surely they don't have that.
They collect uni policies where possible.
Okay, they do sound pretty impressive, but is it not a bit of an echo chamber?
It can be, but ASAP Bio also engage with people who don't love preprints and have concerns. So we had an excellent discussion on this very topic a couple of months ago.
Oh, is there anything ASAP Bio don't do?
Honestly, no, they're so nice over there. They were so quick to jump in and support this show. It's your one-stop shop for info on preprints and open science initiatives, so head over to asapbio.org to learn more and subscribe to their newsletter for the latest in preprint news. If you want a deeper dive into the world of preprints, then look out for the next recruitment of ASAP Bio Fellows. So, I think to get into the preprint part of this, I think it might be actually better to talk about one of the things you said on the little form we get everyone to fill out, which is that one of the things you'd like to improve in academia is the publication process. And I mean, my standpoint for the past few years has been to promote preprint usage. This is one of the ways I do that. There's a whole bunch of other ways. But I mean, how do you envisage improving the publication process?
I again, kind of like with the heart therapy ideas I have, they're kind of crazy and radical.
That's
and
what you want.
I'm not sure if they'll ever happen, but I'll tell you what I think anyway. I mean, when I tell people about the way that the system of academia is broken, I basically just tell them how the money flows.
Yeah.
And I tell them, the publishers, for all of the good that they do and all of the important role that they have, they get money from both the people who provide them with their goods and the people who use those goods. And any other business would never function that way. I sort of use the analogy: imagine you grow strawberries and you go to a shopkeeper or a supermarket and you say, I love your supermarket so much, it would give me an honor to sell my strawberries in your supermarket. So I'm going to pay you to sell my strawberries and you keep the money that you make.
Yeah.
And just so long as you put my name on the packet. And they're like, yeah, that sounds insane. I'm like, well, that's kind of, and then you have to beg other people for money to grow your strawberries.
And you then buy your strawberries back.
Exactly. So the way I always think about these things is incentives. What are people motivated to do? And people also ask me sort of, how did this come about? And I don't know how true this is, but I think, I mean, correct me if I'm wrong, but I heard it somewhere that the way scientific publishing was done hundreds of years ago was it was generally people who were extremely privileged. They didn't do it for their career. They had plenty of money, and it was thought that money would act as a sort of source of corruption in doing pure science and thinking about the world. And so it was heavily frowned upon. And everything sort of seems to have evolved quite badly from this, except for the publishers who do act in a for-profit manner. But they're a part of the system too. So if they can act with integrity in science whilst also making money, then why shouldn't everyone? So the way I see that is therefore, either everybody in the process is corrupt or no one is corrupt. That's, so if one person decides that they're going to be the moneymaker in this, then a scientist is just as valid in deciding that they want to make money as they do their work as well.
Yeah.
And so the way I think about this is it would be great if institutions basically said to publishing houses, listen, we produce work that you go and sell to other people, essentially. We are authors. Maybe one individual author is not powerful enough, but I think an entire institute that provides a lot, or maybe groups of institutes who get together and say, listen, we're not going to pay you to publish our work. You're going to pay us. And you will, like any other business, get your money from the people who read your stuff, which, by the way, might include us, but it doesn't change the fact that at the very beginning, you have to pay for the good. And so I think if there was some sort of mechanism by which, you as a scientist could say, you know what, I work hard to get my salary, right? But my institution should earn money for the work that we as an institution put out there. And it's never going to happen, I don't think. It's way too radical, but I like the idea of it because it's the way it should work in my head.
Yeah. So yeah, we're I'm in the process of writing a little sort of mini documentary we're going to put out hopefully very soon about the whole history of scientific publishing. The current mess we're in is largely due to Robert Maxwell in the 1940s and onwards, made worse by the internet instead of better, weirdly. But yeah, I think that we need the incentives. There are some people who do now, when they get a request to do some peer review, they will invoice the journal before they do that review. And funnily enough, nobody ever gets paid for it. But we should all do that.
Yeah, no, sorry. In my little model that I drew out, I did also put reviewers as another money flow. Because it's crazy. It's free labor.
So where do you find preprints in this whole process? Where do they fit in?
I see them as a catalyst for change, I think, at the end of the day. It's not solving all of the major problems, but I don't think it's solving the problems directly, but it's solving them indirectly in a very effective way, which is essentially, at the end of the day, you want to communicate your work so long as you've got no other reasons to hold it back. And this is a great way to do this. I kind of see it as like one big conference paper poster session that everyone is invited to, right? Because when you see stuff at conferences, no one turns their nose up and said, oh, this isn't peer reviewed. You judge it on its merit, right? So I see a preprint as, and again, I've listened to some of your previous episodes and I've heard about and read about all of the problems that peer review has anyway, and the amount of peer reviewed papers I've read, I'm no exception, just another example of someone who's read plenty of peer reviewed papers and found really like startling errors, and you wonder how it gets through. And so so I just see it as one big poster session that everyone's invited to, and it just keeps things running really smoothly. I love it. But I know you asked this question of sort of whose idea, and my PI is really keen on it. Anything that can go out on we sort of have a bioarchive Twitter dual strategy. I was so surprised when I found out how big a role Twitter played in the dissemination of science. Wow, I couldn't believe it, because normally you hear all about how awful Twitter is and it's the cesspit of human conversation. And when I told people that I'm putting my work up on Twitter, they sniggered. They thought it was hilarious. They were like, okay. But no, people do really sophisticated threads, and so we did that. We did videos and sort of very sort of cut down figures. I think it's great. I think that's another thing that actually goes really hand in hand with bioarchive as well.
Yeah, it is.
Two in combination.
We do need to stop mentioning the T platform, though, because they haven't paid us any money yet for all the free advertising we give them. But it is really good. It is just a nice... It kind of levels the playing field, I think, a little bit, because you don't have to be a big name. You just have to do some really good science. And if you put it out there on Twitter especially, it pretty much finds its way. And then a big name might retweet it, and then you kind of takes off. It's great.
Yeah, no, and I think the more people are in this world of social media science communication, they I think are encouraged to then build their scientific network in I think what is quite a healthy way.
Yeah, I agree. I look forward to the day university press departments finally get on board and start doing this properly and providing a service where they actually help you do all the things that you just said you've done, where you have a nice long thread on Twitter, but you also have a video to go along with it. And you utilize all the mediums available to you to share your science. Because I think that's where I mean, that's where we should have been a few years ago, but I think we're slowly getting there to actually realizing we need to communicate it more than just here's a paper that is not necessarily accessible to anyone who's not a specialist.
Yeah.
Okay, so now I can ask about being a chef. So you said you wanted to be a chef when you were younger. And I find that really, really interesting because my ex-girlfriend, really, really good cook, should have been a chef, really. So, but because of that, she was kind of always thinking about being a chef. And when you look at the career paths, they're so remarkably similar. Like, you work with a big name, and that's how you then kind of progress into running your own restaurant, and it's just remarkably similar. So how did you go from chef into science? Was it actually just, it was so similar, it was just obvious? Or was it just coincidentally similar?
Well, I mean, in terms of the way that the career works, no, I don't think I certainly didn't say, oh, they're so similar, I'll have just as difficult time running a restaurant that I would running a lab. Basically my dad said to me, when I was really, really keen on I don't know, looking at patisserie schools in Paris, like really trying to like be like, if I'm going to do this, I'm going to do it properly. And he was just like, go to university, get your degree, and then after that, you do whatever you want to do. Yeah. I'm like, all right, okay then. And fortunately, I was interested in academics, so I was very happy to go along with it. And I did human genetics. And I was just blown away. And I was like, you can cook, you have to cook to eat. You can do cooking in your spare time when you have time for it. And that can be a fantastic hobby. It's hard to be a hobby scientist. No one's going to take you seriously. You've got a shed in your back garden with some samples in it.
See, now we're going to get letters from all those people who can hack themselves and think their lab garage is a real lab.
They're always welcome to post on bioRxiv, and people can comment all they want on that. That's the point, I suppose. But there is a website where they do post a lot of stuff. I'm curious to know if anyone's studied them. I think that would be quite interesting if you sort of, as in, reviewed their own results and in a more independent manner tested whether they're going to live longer or not. I
mean, yeah. But also, they're more, as a community, they're quite open. So maybe we should be looking at them on how we share stuff.
Yeah.
We're doing it wrong.
That's true.
But so before you came into science, you were in business. So again, kind of, you didn't take a direct path, which I always like. So could you talk a little bit about what businessy stuff you were doing? Businessy stuff's not a great term.
Yeah, no, sure. Again, the same thing happened. The same conversation with my dad happened after I finished my undergrad. I decided to do a master's because I was still not really sure what I wanted to do, which area of science, and it was in nanotechnology and regenerative medicine. And I was like, that sounds awesome. So I was like, if the purpose of doing a master's was to kind of give me exposure to a field I might want to go into. This was the right one. So I did that. And then my dad said to me, you should really try and apply for PwC. They're a good company. Just try it. And, get your feet wet in the world of business. And then after that, if you decide, you can do whatever you want. I was like, if you really don't bother me after this one, fine. So I agreed with him that, the world of science is one where business acumen is very poor. And I think that's half the reason why we're probably in this sort of publication mess. And so actually I thought, it would be quite interesting to spend a few years getting some experience in this. I worked in the management consulting branch, and I kind of ended up working a lot on hospitals and health projects to try and stay somewhat close to interests. And it was actually a really interesting place to be. And I didn't realize how complicated the health system was and how the money flows. But actually, it was a great experience and I really enjoyed it. I got to work on, optimizing operating theatre performance and stuff like that. So, it was great. Some days we would get on the train, go to a hospital, observe some surgeries, and because you really had to understand all of the measures that went in place. So you could go away and start identifying where things could be cut out, sped up, and those sorts of things, so they could get more people treated in a day. So that was actually a really good experience. But I knew it just wasn't. It wasn't where my passions lay. It was too far from it. Yeah. And I thought, what? If I don't decide to do my PhD now, I will never have an opportunity to get back into it. So I sort of, bit the bullet, jump back into academia, as I said I might would, and now I'm here.
Now you're doing a new postdoc. So is your current plan to stay in academia, or have you seen the light and are going to jump ship like everyone else apparently is, according to Twitter?
I'll be careful what I say, but I'm actually very fortunate. I've landed in a lab where the PI is very business oriented. He's already set up several different companies from platforms that he's developed throughout his career. And so he's perfect, in my opinion, he's perfectly situated between academia and business. And he says himself that, he kind of dabbles in both, depending on sort of which he's feeling a little bit more into at different times. But I feel like I'm in a place where I'm in a lab, so the science is taken very, very seriously, but we think a lot about, I like it because the way that the lab thinks is very much just like, okay, let's understand this, but as we understand it, let's also consider how easily it would get through regulatory approval, how easily it could be administered to a patient. And it's not often you find yourself in a place where you can do really hardcore science, but also think about reaching the clinic much sooner than, say, my previous research. So I don't know what I'm going to do afterwards. I don't know if it's with a view to opening my own company, like a startup, or to join one, or to open up a lab that kind of does a bit of both. I really like the idea of that, but I definitely like the idea of having some sort of business push in science. I don't shy away from it as something that is, to be shunned.
I think it sounds like a really nice way of doing it, to have a nice focus on not just discovery, but how it's going to be applied. I think it's often missing in science. We get a bit too wrapped up in this does this, so let's look at it, and not how can we use it.
I mean, I'm in the process now. I've only been here a few weeks. I'm spending most of my days just thinking and sort of scribbling out ideas on paper. And the amount of times I come up with a crazy cool idea, but then it's just like beyond a paper, that's not really applicable. And it in a set. I mean, I'm a big advocate of basic science. My previous institution was one that was heavily into basic science research, and it's definitely something that is absolutely critical. You need that knowledge fountain. But I do like thinking a little bit more of how would this be used. So it's a good place.
Good. Sounds like a good place.
It's really interesting, actually, the whole business side of it. I think I've never really thought about it like that, but I guess that's what they're trying to get with like lots of translational medicine. So whenever I write something, it's always how will this affect patients?
Yeah.
Not necessarily in a business, but like how can this be used, rather than I'm just looking at stuff. But you're right, we do need the knowledge fountain of basic science as well.
Yeah, of course. It's like the way I explained it to my girlfriend at the time, now wife, in terms of sort of why you would even bother, as someone who wasn't in science, a lot of questions I got from her was about sort of when are you going to see the fruits of your labor? Because it's hard to try and excite someone about, I don't know, like transcription if they have no interest in science. You're never going to get someone to just be purely in awe of biological processes, even if they're unbelievable, and you'd happily spend your life studying them if you could. And the way that I think about it, and I explained it to her at the time, is that it's almost like the more basic your science, the more people it will affect, but in a much longer period of time. And I always think about the, structure of DNA. At the time, had very little applicability, or at least in the ways that we necessarily think about sort of, okay, you found the structure of DNA, like what can we do with that right now in a patient? Nothing, right? But it's the foundational basis for every technique that we're now bringing to patients, and it's millions or billions of people it's affected, but it took about 70 years. So if you want to go basic, that's great, because you're going to have a huge impact in a long time. But if you're going to spend your time working on how to get a particular gene therapy into a sort of a population of people who have a rare disease, you could help someone today, but it might be sort of 10 people. I mean, there are always sort of all funny interconnected ways as well, but as a general rule, I see them as both really good because they both have their advantages.
Fun fact about the DNA structure paper, not peer-reviewed.
Right.
Published because the editor liked the people. Back when halftime did it.
I'm not sure how fun that fact is.
Well, we can cut it if it wasn't good enough.
No, it's interesting. Just not particularly fun.
Yeah. But but I also do. I know what you mean a lot. I've heard probably more times than I would want to admit about sort of relationships people have with editors and the role that plays, because it's just like I've heard phrases of, "Don't worry, if we send it there, it will get in."
Yeah.
You know,
you hear that around, don't you?
Well, if you employ the editor of a journal, then you can publish any old crap about hydroxychloroquine, for example. Anyway, let's not get ourselves into trouble.
Let's move away from that.
Okay, and that is the show. If you enjoyed listening, then hit that subscribe button for more and leave us a review on whatever platform it is you're listening on. You can reach out to us on Twitter at MotionPod or online at preprintsandmotion.com. Didn't enjoy that? Well, we're all scientists here, so send us your review and let us know what works or what you'd like to hear more of, or less of. But until next time, have a good week.